right, great. Let's get started. Again, good morning, everybody. Thank you for joining me this morning for a webinar on SolidWorks simulation. I'm Arun Thiraviam. I'm a simulation product specialist here at GoEngineer. Uh, Today, I'm going to spend a little bit of time, walking through a quick or a brief outline of the thermal analysis tools that is built into the FEA capability, the finite element analysis capability inside SolidWorks. So let's get started. So if you've ever used SolidWorks simulation, you've set up a simple study, you can see that you have a set of tools that you can use to virtually test your products. Now, here I have a couple of animations that gives you examples of typically structural performance tests that you run on your products in order to ensure their functionality and performance on field. For instance, we have this little mountain bike fork that we've applied a load on. We're studying the stress distribution. We have a drop test on this little plastic part to ensure that it doesn't crack during the drop process. And we also have this little knee joint that we've run a simulation on along with our motion module. So primarily, the goal of these analyses were structural. You just want to make sure that your designs are light enough, yet are not compromised structurally during their performance. Well, the thermal analysis tool is another really popular tool that a lot of mechanical engineers use in order to not only validate the temperature distribution and the thermal performance of their design, but also to take a look at the structural performance, the thermal strains that are developed, the thermal stresses that are developed across your product as they receive heat. So I'm going to spend the rest of the presentation, like I said, going through the thermal analysis tools built in our FEA. Now, uh, as a brief roadmap, now we'll be touching upon three things, starting off with, say, the mechanisms of heat transfer. What are three, four mechanisms that you need to take into account while evaluating the thermal performance of your products? Finally, we look at two separate case studies, one giving you a brief outline of all thermal analysis capabilities, and another case study that gives you hand calculation validation of an analysis we ran inside SolidWorks. Okay, as far as the mechanisms of heat transfer go, now what are the three forms of heat transfer? Essentially, conduction, convection, and radiation. Let's spend the next couple of minutes kind of deconstructing each of these and see how we can translate this information to the software and see what information we get out of it. Now, starting off with conduction, the most basic form of heat transfer, it essentially indicates the heat flow from the hot end to the cold end based on the thermal conductivity of your system. So typically, uh, uh, a mode of heat transfer for systems in contact. And what essentially controls the rate of this heat transfer are not only the geometric properties like the area of cross section of the direction of heat transfer and the length of the heat transfer, but also a very important quality called the thermal conductivity, which is an internal material property. And as always, heat goes in the direction opposite to the temperature drop. So it always goes from the area with the hotter temperature to the colder temperature. So essentially, if you're running a simple conduction problem inside SOLIDWORKS, now three key variables are you're either specifying the temperatures at the hot and the cold end to see the rate of heat transfer across the product, or you're specifying how much heat is entering the system and what is the temperature distribution of your entire system by virtue of the heat. So you essentially need to define two of these three things. Now, how about convection? Now, convection is a heavily misunderstood concept in the fields of engineering. Essentially, convection is a process by which uh, liquids carry heat away from the system by virtue of mass transfer. Now, although we need sophisticated, fluid dynamics tools in order to capture these kind of heat transfer processes. Now, with the structural analysis software, how convection is essentially defined is you essentially specify the surfaces of your system that's in contact with the fluid. You specify the temperature of the surface and the average temperature that the fluid uh, that is in contact with the surface is. So based on this, uh, the software calculates how quickly heat is transferred between a solid surface and a fluid surface. So, in sum, essentially convection heat transfer tells you how quickly the fluid in your system carries the heat away from the solid entities. Now, since you're unable to uh, uh, model both the solid medium and the fluid medium. You're able to model only the solid medium. What we use is a coefficient called a heat transfer coefficient that gives you the rate at which or that controls the rate at which heat is being carried away from your system. So if you have your iPhone or an electronic component that's sitting around on a table and you have air all around it, as the thing is heating up, you essentially specify all the surfaces that is in contact with the air and the convection coefficient of the surface and the air combination. Now, as far as the convection coefficient goes, a lot of people have questions about how to determine these. There are three primary modes by which you can determine these. Now, you can find tables for convection coefficients for different combinations of fluids and solids. So it usually is a property of, or you have different convection coefficients that essentially specify how quickly heat is being lost to a fluid medium from a solid medium, which is dependent on the individual properties of the solid and fluid. So typically these tables are populated by experiments. So if you have natural convection of air and metal, the heat transfer coefficient can vary from 5 to 25 watts per meter squared Kelvin. Now, if you're an advanced analyst and if you have a heavy background in CFD and heat and mass transfer, you can take into account, through heat and mass transfer tables, what different convection coefficients are for, different velocities and different mediums and so on and so forth. And finally, the most robust way and, the quickest way of kind of avoiding using the convection coefficient but being able to program both the solid medium and the fluid medium in an analysis software is to use the CFD or computational fluid dynamics software that essentially avoids this entire convection coefficient definition. It essentially calculates this heat transfer coefficient for you when you run this sort of fluid solid interaction. And finally, uh, the third form of heat transfer is radiation. It's essentially a mode of heat transfer which does not require any medium between the interacting bodies. So essentially how heat is being transferred here is by virtue of the electromagnetic rays generated uh, from, by virtue of heating a body up. So I have this little equation that describes how much heat, describes the amount of heat that's being emitted by a body that's at a temperature T. Now, today we are primarily going to talk about the conduction and convection modes because radiation would require its own, sort of webinar. So we'll set that aside for now. Now let's talk about the thermal analysis that we're going to solve for today. Now, what we have here is a spark plug, the holy grail of the automobile industry. I mean, what it essentially does in combustion engines is it creates a spark that ignites the fuel, that then drives the piston, that gives you the motor torque. So what we're going to see here is a very simple analysis. Now, based on the heat generated right at the tip of the plug during the sparking stage, we want to see how quickly the heat is dissipated right through the plug. Now, not only that, now as metals and different components heat up, solids heat up, they change shape. So by virtue of this change shape, and you know, you'd like to calculate the thermal stresses that are developed and to ensure that the way this thing is constrained and the way this thing is assembled, it doesn't exceed its factor of safety. So we're going to use the thermal data to run a structural analysis. And finally, I'm going to take you through some of the transient analysis capabilities inside SOLIDWORKS. Now, essentially, what we're going to get is a steady state solution once all the transients have gone off. But if you want to see how quickly the spark plug heats up as soon as the spark has begun, now that's a capability that's built inside SOLIDWORKS as well. Now let's just jump into the software to take a look at how I'm going to run the analysis. I got a little ahead of myself here. So to just establish a goal for this analysis, now we want to see the stress distribution of the component, which is the spark plug, due to thermal loading, which is combustion. Now I'm going to jump right into the software. Now this is my little spark plug I used for this analysis. It consists of four parts. Two parts, one part of ceramic porcelain, two parts that are made of carbon steel, plain carbon steel, and the electrode, which is made of silver. So if you're accustomed to using SOLIDWORKS, you'll understand that SOLIDWORKS is gravitating away from just being a CAD tool to being a complete solutions package. So it has different tools that are built in that tackles tackle issues on different stages of the product development process, such as design, manufacturing, validation, and documentation. So all of these tools are actually available and accessible in the SolidWorks add-ins tab. So once you go into the add-ins tab to add in the simulation tools, all you need to do is click the SolidWorks simulation button. Now that loads in the FEA solver, and that lets you set up different virtual analyses to verify the thermal, vibration, and structural performance of your product. Now, as soon as I hit the add-ins tab, now I have this little, simulation ribbon, and I have this little study advisor. Now, activating this, turning on study advisor gives me a buffet of simulation tools that I can use in order to study the structural, vibration, and thermal performance of my designs. Now, just to set up a simple structural analysis, uh, I can select the thermal tab and hit the green check mark, and a couple of things happen. Much like the CAD site having a feature tree that gives you the history of all the components that went into, or the history of all the features that went into building up the geometry of the design, the analysis has its own simulation tree, has its own feature tree. So we go in, specify each item on this tree, and you're set for the analysis. So I'm going to jump into an analysis that I've set up. You'll notice as soon as I set up any analysis, it piggybacks on the model. So I have an analysis that's set up, prior to this little webinar. Um, so the first thing I do is specify all the uh, material properties of the components. Now for the material properties, I can head into my SolidWorks database that has all the physical and the mechanical characteristics in order to run different analyses. For instance, you have the elastic characteristics to run stress analyses, and you have thermal characteristics to run the thermal analysis. So here the thermal conductivity is about 43 watts per meter Kelvin for plain carbon steel, while for ceramic porcelain, the thermal conductivity is about 1.4. So once you have all these material properties assigned, we directly jump into the thermal loads. Now for the thermal loads, we made an assumption that the tip of the spark, or this region of the spark, the spark plug, essentially experiences the temperature of about 1000 degrees Fahrenheit as soon as, or during the sparking process. So we can set up these boundary conditions by right-clicking the thermal loads item on the tree and picking the kind of boundary condition that you'd like to specify: the conduction conditions, the convection conditions, or even the radiation conditions. So initially, I specified. I've essentially mentioned to the software that, hey, all of these surfaces are going to be held at a constant temperature for the duration of the analysis or the duration of the spark. Now, in order to close the loop, I essentially need to specify how heat is being dissipated by the outside surfaces. So there are two key surfaces here that are in the spark plug. The set of surfaces that are close to the tip, that's essentially screwed into the engine, into the into the cylinder head, and these set of surfaces that are cooler, that are exposed to the the empty space inside the combustion chamber. So essentially, these surfaces are going to lose heat to cool air at a specific rate, and these surfaces are going to lose heat to a solid that hasn't been modeled, but we understand how quickly it's essentially losing heat to it. So heading into one of these convection menus lets you pick all the surfaces where the convection process is taking place, the rate of convection, which is through the convection coefficient discussion we had prior to starting the webinar, and the temperature of the medium that it is exchanging heat to. So what drives heat transfer is essentially the delta between the surface temperature and the pseudo bulk temperature. So that's the bulk temperature. In the same fashion, looking at the convection conditions of just um, the this area or the surface of the spark plug that's in contact with the cooler air, you can see that the ambient temperature is a lot lower and the rate of convection is a lot higher. Okay, great. Now, once this is done and you set up the mesh and you run the analysis, the reason you run such an analysis is to essentially see the temperature distribution. So take a look at the temperature distribution. You can see that the tip of the spark is at about 800 Kelvin, while um, close to the contact area, the plain carbon steel, the heat dissipates at a very rapid rate and it goes down to about 366 Kelvin. Now, as far as the post-processing tools go, you aren't only limited to looking at the temperature spread on the surface, you can also take a look at sections to figure out how the temperature varies right across a section. Now I'm going to use a combination of this section and the probe tool in order to probe the different temperatures right across the center. So plotting this essentially gives me what is the kind of temperature drop right through the cross section of the spark plug. So you'll have to bear in mind that this will have direct effects on the structural performance of the product, and you'd want to minimize this little delta as much as possible. Now, moving away from just running a structural analysis, in order to set up a structural analysis, you use the static study item. And setting up the static study item, you specify a fixture. Right here, I've applied one fixture that is going to prevent the spark plug from moving. And in order to assign the thermal load, you'll need to borrow the temperature distribution from the thermal analysis that you've run. So essentially, for all the thermal analysis that's been run in this study or in this specific component, there are three. I'm going to use the first thermal analysis that I just demonstrated to you. So what it's going to calculate is the delta between the reference temperature at zero strain and the existing temperature distribution to calculate the thermal strains. So of course you take a look at, you can get an idea of the stress distribution and the displacements of the different areas of your component by virtue of this temperature delta. Now besides this, heading back into the transient analysis, now in order to set up a transient analysis, all I need to do is specify that I'm running a transient analysis, how long I'd like to study the system for, and how often I'd like for the system to run the calculations for. Of course, the smaller this number, the more transient data you get, but the longer it takes for the analysis to run. Now just quickly, and besides, a very important aspect of the transient analysis is specifying what the initial temperature of the system is. Now I've set this system to have an initial temperature of about 40 degrees Celsius. So essentially the entire system starts at 40 degrees Celsius. As soon as this 1000 degree Fahrenheit is introduced instantaneously to these dips, I'd like to study how quickly the temperature grows in a matter of 7 seconds. Just going back into the presentation to just briefly summarize all the results that we've seen. So you can see that the first thing we get is the temperature distribution on the surface through a thermal analysis. Now, by probing the different points of the system, through a little pattern right here, you're able to see how quickly the temperature drops from the tip to the electrode. Besides, there are two other pieces of information that we get from this analysis, which is just the structural performance. Now here, this is about 2200 megapascals. I mean, even the minimum is close to about 550 megapascals, which is over 2 times the yield strength of plain carbon steel. So this indicates that the factor of safety is extremely low, and this current spark plug design has a tendency to fail during its performance. Now, as far as the transient analysis goes, what I did was I picked one point on the system to essentially see the growth. So I'm able to see these kind of responses with time. So with 7 seconds, the tip of the spark plug essentially grows from 40 degrees to about 200 degrees in 7 seconds. That just gives you a brief idea of the capabilities. Now let's go into the analytical validation. For the analytical validation, I've set up a really simple problem. Now, typically in industrial piping, insulation becomes a big aspect because all of these pipes carry really hot fluid, and you wouldn't want the fluid to cool down during the transport process. So what do? You stack up insulation around pipes. Now, essentially, the goal of this analysis is, hey, how do we determine what the critical insulation thickness has to be in order to make sure that heat that the copper pipe does not lose heat to the surrounding. Now, why is this such a big deal? Because we are trying to minimize the heat loss to the surrounding, but this entire heat loss process is a combination of conduction and convection. So as you increase the thickness of the insulation, there are two conflicting thermal effects. Now, increasing the conflicting thermal effects are, as you increase the insulation thickness, you increase the thermal resistance by conduction, so you minimize the heat loss. But the external surface of the insulator is exposed to the air outside, so you reduce the thermal effects of convection. So these are little formula that essentially tell you the thermal resistance. So the higher the resistance, the smaller the heat loss, as indicated by this equation. So increasing the insulator thickness increases the the conduction resistance across the thickness, but it reduces the convection resistance because of the larger surface area. So because the surface area increases, a lot more heat is lost to convection. So since these are opposing effects, there is a critical point where both of these meet, and you can significantly reduce the heat loss as indicated in the previous slide, such as this. Now let's just jump into SOLIDWORKS and take a look at how I've set up the analysis. Now, as you can see, now this is my little assembly. Here I have the copper tube that's surrounded by by the insulation, the OD of the insulation being 44 and the ID of the insulation being 32. Now for this initial design, how I've set the analysis up is I need to specify the thermal conductivities of the insulator. Now with SOLIDWORKS, you're not constrained to sticking to just the standard materials. You're able to customize materials as well based on, the thermal and the mechanical characteristics they possess. So here I have an insulator material with the thermal conductivity of about 0.15 defined. Now I apply this material property to the insulator. Now after this, as far as my boundary conditions go, now I know the temperature exchange between the fluid inside the pipe and the copper tube is essentially 27.5 degrees. So the fluid flow and the temperature of the fluid maintains the temperature of the copper tube at 27.5. So I've applied that as a boundary condition to the entire volume. Now, as far as the convection of the insulator goes, now based on tables and experimental, experimental verifications, I've determined that an insulator loses heat to the surrounding air at the rate of about 6 watts per meter square Kelvin. So that's my convection coefficient, which is a big assumption. A More often than not, this convection coefficient is not uniform, but I've just assumed for all practical purposes that it's uniform right across the surface. Now on running the analysis, of course, the first thing I get is the temperature distribution. Now just moving away from conventional outputs like the heat flux and the temperature distribution, what you'd essentially like to see is, hey, what is the heat being lost right at this surface? So to get the heat loss, now if I go into the results item and I hit list heat power, I'm able to grab the surface that I like to study the heat loss for, and I'm able to probe the value of that heat loss. So if I change this to a unit system that I'm more accustomed to, which is watts, now this indicates that with this current insulator thickness, my heat loss is about 2.1864 watts. Now you may ask me, hey, how do you know that this is right? So that's essentially the goal of this analysis as well. Now I want to try and validate this value that I see, this heat loss value, through simple hand calculations. Since this analysis is simple, it's a symmetric analysis. You have predictable geometry that you can write equations for. I was able to run simple hand calculations to essentially try and validate that number. So just jumping back to the presentation to take you through what that validation looks like. Okay, as we discussed, the heat loss is essentially a function of the temperature drop from the copper to the insulator. Essentially, the insulator is exposed to a 50-degree environment and the copper is 27.5 over the thermal resistance. Now, the thermal resistance here is a combination of the conduction and convection resistance. Now, as far as the empirical formulae for the conduction and convection go for this sort of concentric piping system in contact, these are the formula. So they have a combination of the geometric properties of the pipes in contact and the thermal conductivity of the insulator, and the convection coefficient. So plugging in all these values, and calculating this out, now I get the total heat loss from the insulation to be 2.186 watts, which essentially matches with what I see with SOLIDWORKS. Okay, great. Now that I've validated this analysis, now that I've justified that, hey, I actually have a realistic analysis here. I'm able to calculate the heat loss with pinpoint accuracy. 2.1864 and 2.186, I'd say that's about 100% correlation. Now what I'm going to do as a next step is kind of vary the insulation thickness and see how that affects the heat loss. Now in order to do this variation, of course you've seen this multiple times, I'm going to utilize the design study tool inside SolidWorks. That's essentially the structural design optimization tool that's built into SolidWorks that lets you vary a geometric parameter. For instance, I varied the OD from say 39 millimeters to maximum of 64 in a step of 5 in steps of 5 millimeters. So during this variation, actually I'm able to get the software to track what the resultant heat flux on this surface is through that analysis and what is the change in surface area. Now, with the design optimization tool, I have the ability to stop right here to run just what if analysis, set up design of experiments, or I can take this to the next step and specify a goal in order to calculate the thickness that minimizes the heat loss. I haven't done that now because typically I want to show you some of the post-processing and the graph extraction, how you extract graph from such what-if analysis. So I, left out the optimization. But let's take a look at what this looks like in the software. So essentially, like I said, I have the variables defined and I have what I'd like to monitor as I'm changing these variables inside the software. Yep. To set up a simple design study, now I can grab the design study tool from the simulation study advisor again. If I hit new study, the design optimization tool should be the 8th item on the tree. As soon as I grab the design study tool, I have this little manager that pops up. Now this little manager, like I said, I need to specify the variables and the constraints. As far as the variables goes, I've already specified a variable that grabs the outside diameter, but I can very easily add parameters, adding different geometric properties. So this is actually a multi-variable design optimization tool. So I can have multiple variables in order to come up with an optimized design. I just decided to stick to one variable in this one. So once I add the outer diameter, I'm going to specify what my min and maxes are. Now I'm going to have a minimum of 39 and a max of about 66. And I'm going to step these, or actually I'll set this to 69. And I'm going to step these in steps of 5 millimeters. Now finally, I'm going to add a constraint. So adding constraints to the analysis is just a matter of adding sensors. So what you do is you're able to add these little sensors that track the simulation performance parameters such as stress, strain, displacements, and thermal data for different areas on your model. So in that fashion, I've set up about 3 or 4 sensors that tracks the temperature and the resultant heat flux just from that surface. Now, as soon as I set up a sensor, all of these sensors essentially sit in the sensor folder, which I've defined beforehand. So I'm going to look at the resultant heat flux. I'm going to monitor the resultant heat flux from the thermal 1 study that I've just set up. And finally, I'm going to monitor how the surface area changes by virtue of the change in the geometry. So as soon as I have both these set up and I uncheck the optimization button, I'm just going to hit run. And what you'll notice, SolidWorks, what it does is it kind of varies dynamically the outer diameter, and it runs an analysis on what it runs a thermal analysis for each of these scenarios. Yep, once I have the 8 scenarios defined and simulated, give me a second. There it is. So I have a table of values, a table of thicknesses for which I have the resultant heat flux and the surface area. Now these are typically useless unless I'm unable to graph these. So I can define little design history graphs that essentially look at how my heat flux changes with with thickness. Now you can see that this is sort of parabolic, but what I'd essentially like to see is what is the total heat loss, and that's why I calculated the surface area as well. Now I can combine the two with an Excel sheet by hitting the save button. So that saves a little CSV file for me. So once I save the CSV out, now once I fire up Excel, and I access the CSV file, I have all of these resultants available to me. Now to study the exact heat power, I essentially need to multiply the heat flux by, sorry about that, multiply the heat flux by the surface area. So essentially this gives me the heat flux with respect to thickness, and if I'm able to quickly plot this graph out, you can see the little heat flux variation. Should I get that point? There it is. The heat flux variation that shows you how the heat power across the insulator, the heat loss across the surface of the insulator changes with increasing thickness. So essentially you'd like to be to the left of this side of the spectrum, to the right of this side of this thickness. So this would be your critical thickness, and essentially you'd like to add insulator thickness. You know, you'd like to add a thickness beyond the critical thickness in order to make sure that in order to minimize the heat loss. Um, just jumping back into the presentation. So through this little design study, we were able to justify what the critical insulator thickness is. So if you are in the insulation industry, you can run this similar analysis through networks of pipes to kind of figure out what is the insulation thickness you need to add in order to go over this critical and to minimize heat loss. Now to quickly summarize this presentation, what we took a look at is how we use the integrated thermal analysis tool inside SOLIDWORKS to solve simple, structural effects due to temperature distribution. We ran a little design study that showed you how you can automate analyses, uh, and graph out results that give you information about how changing a specific design affects the thermal and the structural performance of your system. And finally, we ran a little analytical validation where we validated with hand calculation what the actual design, what the uh, hand calculated values with what we see from SolidWorks. That's about it. Hey, thank you for joining me on this webinar again. I know we went a little bit over time. Uh, and please feel free to write to us if you have any feedback on these webinars and if you'd like, to see a specific topic presented. Also, the reference for these little case studies are in the description of this video. Again, hey, thank you guys for joining me.